I'm Jeet from MIT, and today I'm presenting our work on certifying the robustness of neural networks against a family of semantic perturbations. This work was done in collaboration with the MIT IBM Watson AI Lab. So given a neural network, we know that for a correctly classified point, if we add some small adversarial perturbation, it results in misclassification. Given the existence of several adversarial examples, the task of certification is to find a lower bound such that for any adversarial perturbation of magnitude less than this bound, we are ensured that the neural network does not give a wrong output. However, most of the work in the certification currently is done in the LP norm threat model, which is L1 and L2 balls. And in this work, we want to extend this to semantic perturbations like lighting changes, rotation, occlusion, etc. So, unlike LP balls, semantic perturbations form highly non-convex trajectories in the pixel space. And these cannot easily be certified by using the current LP norm certificates, as the current LP norm certificates only cover a small portion of this trajectory, like the L2 norm ball here covers only 2 degrees of rotation. And not just that, even the best possible LP norm ball we could fit inside these distant boundaries would also only end up covering at most 10 to 15 degrees of rotation, while the attack bounds for rotation are somewhere around 45 to 60 degrees. So we see there's a huge gap that cannot be met by using just LP norm methods. So LP norm methods are not enough to certify semantic perturbations. In order to certify semantic perturbations, we need to ensure that this inequality holds for all points within the semantic perturbation set. That is, the neural network output for the predicate class is greater than the neural network output for any other class. In order to do this, we solve this optimization problem for linear relaxation of a network that is valid around the perturbation set. However, in order to get this linear relaxation of the network, we need to have a very good description of the perturbation set, which is generally hard to achieve, as for semantic perturbations, the perturbation set is highly convoluted on the highly non-convex trajectory in the pixel space. So in order to do this, we observe that most semantic perturbations like rotation can be decomposed into these attack parameters like the angle of rotation, and then we can encode our transformation into these SP layers which have general activation functions and are manually created for every transformation, so that it takes as input the attack parameter like the angle of rotation and gives as output the perturbed image. Now preparing this with our original neural network, our certification problem boils down to being able to certify that for all values of the angle in the attack interval, we are able to certify that this joint network always gives the correct output. This is better as now the input constraint set is the attack interval, which is a well-defined constraint set, and as a result, if we find relaxation in this whole network around that constraint set, we're able to certify the semantic perturbation for the original network. But doing this incurs few new challenges, as forming relaxation for a trajectory is same as forming relaxation for the whole convex set hull of it, which can have some bad regions. As a result, we require some extra work which we call refinement, which is here is the explicit splitting, where we split the trajectory into smaller chunks and certify each of these chunks separately, which together gives certificate for the whole trajectory. And this avoids the problem of having too big of a convex hull, but at the cost of having to run the algorithm multiple times, one for every split. So this gives us multiplicative increase in the cost. However, this is not the only kind of problem we encounter. Another problem we encounter is when we try to relax the SP layers, we end up relaxing too much to get a highly really big region for the trajectory, which can contain some non-robust regions in it. As a result, we need to find some kind of refinement to deal with this as well. So in order to save time, we don't use explicit splitting. Instead, we suggest implicit splitting, which divides our constraint set into these smaller intervals and represents it as a union over these intervals. And then we find a relaxation of the neural network over all these intervals at the same time, which gives us a good certificate while only incurring additive extra cost. And using all of these techniques, with just using the spillers, we're able to get an 8 to 50x improvement over using LP norm balls, and then using refinement, we're able to almost completely close the gap between the certified bounds and the attack bounds. Moreover, this also scales pretty well to high dimensional perturbations like brightness contrast that we show here. But in this case, we see that the attack bounds are very close to the given certified bounds. Thank you.